Okay, let us start today's lecture. First of all, we recall what was discussed in the earlier this week. Okay, we try to recall what it is. The state space design. This technique is based on a matrix algebra. Okay, in the last lecture we talked about how to calculate different operations on the matrix, right, especially the inversion. The important point to notice is that if we are given a matrix A, and then its inverse is equals the adjoint matrix of A divided by the determinant of the matrix A. And then we also look at the construction of the matrix equation. From a given transfer equation in the S domain. We notice one thing that is very important is that for the same system, the state space representation can be different. And then the difference helps to analyze or simulate the system. In order to investigate the system performance. And then earlier this week we saw two approaches from the same given the transfer function arrived at two different forms of the state space equation. Now we look at the third approach. Okay, for the third approach, we use the same example, right? If we are given a transfer function, it's the same as in the previous examples. For this approach, we start with the partial fraction separation. We separate GS by partial fraction. The partial fraction method was used when you carry out the inverse Laplace transform. The essence of partial fraction separation is that we change multiplication to addition. So first of all, we need to factorize the denominator. Okay, we factorize this term. Then we have the S equals minus 6 squared, and then divided by 2, so it is what? Minus x minus 36 minus 32. So it is this 4. So what is it? This minus 2 and minus 4. Thus we have s squared plus 6s plus 8 equals s plus 2 and then s plus 4. So in partial fractions we have the denominator, right, containing all the terms. Then the s squared plus 3s plus 1. So it is equal to, separating the terms, it is a plus b, s plus t plus c, s plus 4. So here on the left hand side we have the multiplication. And then here we have the addition. Okay. Then it is a bit tedious, right? But we can do it carefully. We have to find out the A, B, and C. Okay. So we have to find A, B, and C. So if we multiply the A with s plus 2 and s plus 4, then we have plus B and then multiply with s and s plus 4 plus C is s plus 2. And then the denominator returns to this. Then we equate the terms or collect the terms for A, B, and C. So we have A square A plus 6 is A plus 8 of A. And then divided by the denominator. So we collect the terms. We have the S square A plus B and C plus again divided by the denominator. Right. Then we compare with the original expression in the numerator. Okay. Compared to numerator. Which is S squared plus times 1, okay, plus S times 3 plus 1. So it implies that A plus B plus C equals 1, 6A plus 4B. So we compare our term by term according to the order of the S variable. Okay. Okay, from the term, the last term equals 1, then with A equals 1 over 8. Okay, from A plus B plus C equals 1, then we have N as 6A plus 4B. Then it is equal to 6 over 8. We substitute the A there, and then plus 4B. So we call this equation 1, call this equation 2. And then we multiply minus 4 to equation 1, and then we add equation 2. Okay. So we have minus half minus 4b minus 4c equals minus 4. And then we add to equation 2, we have So by doing that, we can eliminate the variable b for the time being, and then we can calculate the variable c. Right, so that we have 1, 4 minus 2c equals minus 1. Then 2c equals 1 plus 1, 4. And then c equals 5 over 8. Then we go back to a plus b plus c equals 1. Then we have a is 1 over 8 plus b, and then c is 5 over 8 equals 1. Then we have 6 over 8 plus b equals 1. Then b equals 1/4. Then the transfer function in partial fractions so it becomes g of s equals y of s, and then the input so we have this form. Okay, up to here, any question? Up to here. We changed the sense of this method is that we change the multiplication to addition by making use of the partial fraction procedure. Okay, then we continue. So we consider a general form. So if we have the y of s and the us in this form, okay, in a simple form, then we have the y of s equals u of s, and then b, and then s plus a, and then it is also equal to we go back to the use of the s minus 1. Okay, it is an integrator. Then we continue further. Then we put the denominator multiply with the ys. Okay. Then ys plus a s minus 1. Then the y of s equals to b s minus 1 here, s and then minus a s minus 1. So it is equal to equals a b, okay, s minus 1 e of s minus a divided by b, and then this. So in then the block diagram. So we have the ys equals a multiplication with b, and then a integration. So we have the y of s multiplied with b, and then another integration. Yeah. Okay. We write it again. So it is b s minus 1 bracket e of s minus a b, and then y of s. Okay. This one? You mean this one?
Yeah, so why is that on the right-hand side and not? What is that
From the a general expression of the transfer function, a simple form, if we have this, okay, and then we can arrive at this expression. Okay, is that okay at this stage?
why? Okay, why do we want to get at that expression first?
Why we want that expression?
Yeah.
So in the construction of block diagram, we always want the integrator action. So we change every s variable, try to change it to s minus 1.
Okay. So then now when you keep going,
Mm-hmm.
you have ys equals b as the negative 1 times the quantities us minus a over b ys down below what you just wrote.
Mm-hmm.
So why is it ys? Why do we have ys on both sides of the equation? Is there an advantage to that?
It helps us to construct the diagram, right? Just as simple as it, because it involves another integration of the wires. Okay. So we want to put this integration together with another integration. Okay. So here we try to put the integration together on the right-hand side of the equation. So from the block diagram, we see that on the left-hand side of the scaling b, so we have 1 over b of ys. And then on the input, we have the u of s. The input of us equals the combines with the negative of the a, okay, multiplied with 1 over by. So it is minus a So at this point, we have this term. Okay, see this, how we, it is y is. So from this expression, we can draw the block diagram in this way. Okay. Okay, then we look at how we can construct the block diagram for the complete system. Now the transfer function is, so for the first term, we have a integrator, and then we multiply with the scalar. So it is the first part. So agree with this. And then for the second part, the s plus 2, and then a scalar. Right. So this is in fact for the second term, this is for 1/8 of s, and then for 1/4 s plus 2. So it is that we have b from 4 and then a equals 2, as in the previous form. Okay, remember that is from the form s plus a. Then we substitute the numbers, right? Then we have the integrator, and then we have 1/4, and then we have minus 2. And then there's some input and output. Okay. And then for the term 5/8 s plus 4, then we have another b equals 5/8, and then a equals 4. It is also in this form. Then we have the integrator. The scalar function, and then the addition of the minus 4, and then some input output. Okay. And then we go back and look at this, right? These are the additions. It means that, okay. So the addition of partial fractions additional particle in block diagram form. Then the block diagram could be a bit complicated, right? And then we do it carefully. For the first term, we have 1 over s, and then it goes to 1 over 8. And then for the second term, we have 1 over s, and it goes to 1 over 4. And then we have minus 2. And then add together. And then for the third term, we have 1 over s. So it goes to 5 over 8. Here with minus 4. Add them together. Then the key is that here we add the 3 terms together. And that is our y of s. And then for the input, is all combined together. Okay. So is that okay at this stage? Yes.
Previously, when you were doing with the U of S and Y of S,
Mm-hmm.
you made that block diagram, and not on your previous page,
This one?
yeah, so where's the, you just move the equation just above that. So outside of that equation, you've got b s minus 1.
Mm-hmm.
Why wasn't that included in the block diagram?
So y is the b. Okay. B, y is here. The u of s goes through this. It is this one, and then multiply with this one. Yeah. That's part of the signal that the u goes through. And then for the second part, it's this path. Right. Okay, the combination of US is because GS equals Y of S, and then US equals 1 over 8S plus etc. etc. Okay, then Y of S equals U of S multiply with everything. So it is an external multiplication factor common to all the terms. So the signal of US go through all the branches. Okay. Now, we define the states. Okay. Then we define states. With respect to integrators. So we call this point x1 and then this x1 dot. We call this point x2 and then x2 dot. And then the third integrator, we call it x3 and x3 dot. Okay. The important thing is that we define the states with respect to the integrators. Okay, from there, we find out the expressions for x1 dot, x2 dot, and x3 dot. Then we identify expressions for x1 dot, x2 dot, and then x3 dot. And then from the block diagram, so we see that x1 dot equals u, and then x2 dot equals u minus 2x2, x3 dot equals u minus 4x3. Okay, that is from the block diagram. Okay, agree with this? Then we set up the matrix equation. So on the left-hand side with the x1 dot, x2 dot, x3 dot, that forms a vector. And then the matrix, then the variable x1, x2, x3. From the first expression, x1 dot equals u only. Okay, so that independent of the x1, 2, 3. For the second equation, x2 dot is u minus 2x2. So independent of x1, independent of x3, and then related to x2 by the factor minus 2. And then x3 dot is u minus 4x3. Independent of x1, independent of x2, related to x3 by the factor minus 4. And then for the input term, the u, okay, are related to x1 dot, x2 dot, x3 dot. Okay, so we have the 1, 1, 1. Okay, agree with this. Okay. Then the output equation. From the diagram, okay, from diagram, so it is addition of 3 terms, of scaled x1, x2, x3. So we see that y equals 1 over 8 x1 plus 1 over 4 x2 plus 5 of 8 x3. then y equals 1 over 8, 1 over 4, so we have this expression for the output signal y. Okay. Okay, then we are summarize. So if we are given the transfer function, so it is s and then s squared plus 6s plus 8, and then the numerator is s squared plus 3s plus 1. And then we have formulated 3 cases for the matrix equation. Okay, for the case 1, so we have x1, x2, x3 dot. So it is 0, 1, 0. x1, x2, x3. Y equals 1, 3, 1. Then x1, x2, and 3. So this is our case 1. And then for our case 2, so we have the x1, x2, x3. So equals minus 4 minus 1.62, then 1. And then the y equals so this form is quite complicated. And then for the case 3, so we have x1, x2. So it is 0, 0, 0. It's 0, minus 2, 0, 0, 0, and then minus 4. And then 1, 1, 1. And then the y equals 1 over 8. Okay, from these 3 expressions, we can see something interesting. Something interesting. For the first case, see that this, the last one, the last one in the last row in the matrix is this. And then the 0, we can imagine that it is s plus 0 equals s. So here is the coefficients in denominator, and then negative. Okay, see this? Also for this form, it is the numerator. It is the coefficients of numerator. Okay, for the second form, for the second form, it's that it is no apparent relation with transfer function coefficients. Then for the third term, so it is input affects all states. So this B matrix, right, especially it is always 1, 1, 1. Here, this term, this part, the -2 and -4, they are the roots of the denominator. So there are different forms of the state space equation. So we say that the state space equation so it is a vector x equals ax plus b and then u in this form. Okay. The important this measure can take different forms. And then the different forms representing the same system. Okay, any question up to now? Yes?
Yeah, I think one piece is one system over the other, but rather than go through all that work, if we could just do it piece one. Is there a reason?
Yes, there are reasons. Then we need to take a look at the block diagrams. Okay, with a choice of a particular form. Very unfortunately, the choice of particular form is problem dependent. One of the possibilities is that we can consider the simulation structure. So for case 1, so the case 1 is this. So it contains a part. This is the forward. So the signal flows in this direction. This is Y, this is the U. This is the reverse flow. So it depends on the complexity of the system. If we want to separately simulate, right. And then one thing to notice is that especially for the reverse part, okay, it is the denominator of the transfer function. And this part is the numerator. Okay, see this difference here? And then for the case 2 is very complicated, right? And then it is not that frequently used. Then for the case 3, okay, again, the complicated system, 1/8, and then 1/8 is and then another one. Then this is the one. Then it is one part, another part, and then the third part. Then we have the 3 parts implemented in parallel. So if we want to analyze per component of the system, if we want to analyze the S term, or we want to analyze the S plus 2 term or S plus 4 term individually, then this form is more frequently used. Okay. So again, the choice of form is problem dependent. So any question for up to now? Is that okay? So if it is so, then we have to stop here and then take a break and then continue with the interactive tutorial.
How would we know from the problem itself which case we? I know you said just then the difference between the two cases, like between the cases. But would a question tell us if we needed the S's to be like? Is there a sort of form that we need to be told to follow?
No, it is always a design practice. It is always a design practice. It is always a design practice. So which form do we?
Could I see the diagram for case 2 design?
Okay, can I answer this question?
Okay.
You said that they're problem dependent, right? So would the problem tell us? Or would
No. The problem is that, for example, you are required to analyze, right? Analyze based on these factors 6 and 8. Then you choose this form because it appears here directly. So here, if you want to test or you want to analyze the solutions of the transfer function, so it is 2 and 4 that is most important. So you choose this form.
So this one deals with the unfactorized form, and this is the factorized form. That's the difference between the two.
Because the solution S is the solution of the root equation.
So it doesn't matter. Okay, right, thank you.
Okay, no question.
I just want to see the diagram for case 2.
Case 3. Case 3 is this one.
Case 2, no, that's case 1.
This one.
Isn't that case 2?
Yeah.
Case 2.
Case 2 is the one we talk about in the last lecture. This one.
This is one of SEU, right? Plus whatever. But for partial fraction, isn't this a faster way rather than like multiplying additions?
It depends what you want to analyze.
No, just for partial fraction decomposition. So I do multiply, just leave it like that. So I just ignore the denominator since they're the same. These are just the numerators. So find
So
the
it is the same.
Yeah, no,
It's the same.
yeah, same.
method.
No,
Yeah.
just so find the roots. So the roots are 0, minus 2, and minus 4. So I just set s equals 0, substitute. Get at 8a equals to 1. Then same thing, get b, then s minus 4c. So you don't need to do
Yes. You can do it.
you don't need to do simultaneous equations. So you just get the values.
And you can do it this way.
Okay.
You get the same answer.
Yeah,
do you?
but I think it's faster than
Oh,
it is.
depends.
Good.
Depends.
With these cases, where do they come from, or where do you get these matrices? Like, I think it's probably related to.
Okay. It is a matter of defining the variables. Okay, for example, this one, if we define x1 to here. Okay. So the
Then you've got case
equation.
3 here, which I think.
Okay. From the definition of variables, we have this one. Agree?
Yep.
Okay, and then we collect the terms on the left hand side to form a vector. And then on the right hand side, we collect the terms for another vector, x1, x2, x3. Okay. So x1 dot equals u, independent of 1, 2, and 3. So it is all 0.
But just
Yeah.
in terms of different cases, what are different cases?
Well, this refers to the previous lecture, the previous methods.
Okay.
Okay. Case 1 is
I don't think I have the previous lecture.
Yeah, is it?
I don't think I have.
Oh, okay.
So it's related to that stuff. Okay. I'll have a look at that one. Cool. Thank you.
It seems very interested in this topic, are you?
Oh, I probably not super interested. I have an interest. It's fascinating how it all works together, but there's still a lot I need to learn.
Do you find that mathematics is beautiful or not?
I think some parts are nice. Like, I don't have a huge wonder at it sometimes. I think probably other people do more. But some of it's kind of interesting. Yeah.
Yeah.
Do you find do you feel a sense of beauty in maths?
I was proud to say that I find that mathematics is very beautiful.
Yeah. Yeah, I've heard people say that before.
I hope you will find it beautiful when you grow up.
Oh, thank you. Because I asked this year, and then Miss Thomason. Oh, that's the he asked H. Yeah. And then yep. Talks about because I mean, as it is, just like starting off at least, we'll do the point at the maximum share. Yep. And then so that's what it looks like. That's what his looks like, but with respect to the tutor. So that's what no, I spoke to a tutor. Oh, okay. And this is what I was looking at. But he said that because of pressurization, there's also this. It's a horizontal and vertical component on every one of these booms.
Yeah, well, every boom is going to have a combination of different, like every location on that is going to have a combination of shear loads, bending loads, pressure loads. So you're going to have
The pressure load factor is the realization of finding shear.
not necessarily. It won't be it won't affect shear, but when it comes to doing your analysis, like your one license analysis.
Yeah, when you do the loss implement,
Yep.
that would be the intention
Yes. Yeah.
I was also wondering about the actual. Would there be another actual force?
Well, think about the like actual skin piece. So if we so if you've got, between two booms, you've got some sort of skin that's going, if you're imagining that axis, like the plane is like that axis, you're going to have a variety of, you can cut that into tiny piece and just look at it. Which direction will, like, shear, bending, and whatnot be in? So you're most likely your shear is obviously going to be pulling and pushing the piece in those directions. Your pressure load is going to actually be going in and out of the page. So if you're looking at So yeah, if you're assuming,
I thought this would be like straight polymer.
it will be sort of pulled, but it's gonna be pushing it out in order to like do that. So yeah, you've got to sort of think what will your load actually be in what direction. So if you're assuming what are the source again, the simplification of Morse circle, I can't remember which one you assume, but you assume the third axis is zero. You can't do that for pressurization loads. So you're going to have to go through
That would be
sigma 3 in this case.
so when you have sigma x and sigma y,
Yep.
that'll be the shear.
It'll be one of the components of shear. But that'll be well, it won't be sigma 1 or sigma 2, it might even be tau xy in that case, depending on how you
Shear, and then sigma 1 and sigma 2, that would be
sigma 3 will be pressurization. Sigma
that would be for von Mises, right? Sigma 3 is pressurization. When you're doing more circle, it doesn't come out so
well, it's just yeah. So if you look up the formula for von Mises, it's the difference of all. It's like sigma 1 minus sigma 2, sigma 2, sigma all that square stuff.
have that, and when you're making the more circle initially, when you factor into the pressurization rate, it's give you R and
Well, yeah, your sigma 1, 2, and 3 locations are going to be. So you're going to get essentially 3 circles, right? For more circles, all the stuff we've been doing in class assumed only 2-dimensional Moore circles, but in reality, you're going to have 3-dimensional Moore circles. So depending on how you want to compare it, whether 1 and 3, or if you assume 2, 0, 1, 0, 3, 0, depending on how you want to do it, it will determine the locations of the points on the circle. So if you've got, a sigma 3 of something with a tau of something, you're expecting that to be some sort of location on your 3, 1 circle, for example. You said that all your bending is going to be in sigma 1.
So right, so for initial, so you're saying that sigma 3 would be based on the pressurization limit, you'd add it to the Moore circle, like it'd be here, but it would be through it. So because what you're saying, if it's an axial, and then when you compare the shears from the shear flow,
Yeah.
it wouldn't factor into the equation.
Well, it depends on the piece you're looking at and the orientation of the piece and the forces through that specific piece. Like if you've got a fuselage piece which is completely in line with the plane, both its longitudinal direction and its radial direction, then you're going to get the pressure out that way. But if you go and turn the piece into its into the form where you've turned it at 30, 40 degrees or whatever, and you get the shear loads become zero. For example, at these two locations, here, then it's going to completely change how your approach the question. So you might not even have to use Moore's circle to actually do your von Mises analysis, because if you've got your sigma 1, sigma 2, sigma 3, or some breakdown of it, and you'll have tau xy, tau yz, and tau xz. You might already have enough information to actually just solve von Mises without doing a Moore's circle. No, but often it just makes it easier. Like the reason people do Moore's circles is because you have a piece with those components, for example, and you rotate it into a piece with just those components, and it's much easier because von Mises just becomes a difference in stresses, like a bending stress value.
That's what I was trying to ask before. For this piece, the axial load comes out of the plate.
Yeah.
Use that part of the calculation.
Not necessarily. You'd have to do a 3-dimensional problem and be comparing the Moore's circles on all 3 sides.
I think I remember that from the
Yeah, so I just stick to finding what your 1, 2, and 3 values are, your x.
So you don't take into account the axial load when you're creating more stuff. Like is that what it is? Like you don't take into account that it's 3-dimensional.
If you're assuming the pressure load is small enough that it doesn't, then you can just do a 2-dimensional analysis. But if it is going to count, you're going to need to do a 3-dimensional analysis.
So it depends on how big it is compared to how big the shear flow is. I think because the tutor told me that. The tutor told me. Well, I mean, I should have shown you. But probably going to be fairly hard to do, and also, like you said, there's an extent that if this is the wings here, then the pressurization load has a vertical and horizontal component for each individual group.
Yeah, well, that is a way that you could represent. You could break down your pressure load at each boom location into X and Y components. If it made it easier to do a more circular pressure, like if you were going for a more circular approach, you can break down each of them, into their X and Y components. Where so some of them, for this one, if it's on this side, the pressurization load is always completely going to be in the Y direction. Oh, sorry, the X direction. But obviously up here, all in the Y direction. And in some other components, there's going to be, some breakdown of that plus that. So it just depends how you want to break down your analysis. Do you want to deal with pieces around there or pieces? Sorry?
Because you're saying it'll cross out because they're all going in opposite direction. Yeah, but it'll still change the number.
The forces over the whole thing will, yes, technically cross out. That's why you don't have your whole fuselage essentially moving. So they're all in equilibrium. However, yes, it is definitely going to affect each piece.
So that's why I wasn't sure when you said that it doesn't.
No, I worked out the before, and I was thinking of using also to apply. I'll just what we drop. How you do it? It's like I don't know which direction.
Yeah, I just stick to finding all the 1, 2, 3, and then the shear 1, 2, 2, 3, and 3, 1 values based on just 3-dimensional piece, and just do a von Mises analysis of that.
Instead of
Well, you don't necessarily Moore circle is just a simplification of the von Mises analysis.
instead of I mean you'll still have to do this.
Yeah, you'll essentially you'll still have to break down, get all your bending loads, bending stresses, your shear loads, shear stresses, and your pressure loads and pressure stresses, and apply them to each and every piece to find the worst pieces. Like obviously bending is going to be huge shear is probably going to be huge around the sides. So where's the bad point? Probably somewhere around here, because your pressure load is huge, your bending is somewhat critical, and your shear is somewhat critical. So it just depends how you guys want to go about it. Yeah.
Do we include the Excel spreadsheet that we use?
It would make our lives a lot easier when analysing your work. And instead of having to submit 20 to 30 pages of appendices to actually justify your calculations, that's an appendix in itself.
Sorry, you
Sorry?
say something before it.
No.
So just sort of make sure you still have to account for all the pressurization loads in this fuselage idealization.
Once you idealize it, yes, you will need to incorporate pressure loads when you're doing your von Mises analysis. It depends on the failure mode. Also,
You wouldn't have to do it for your shear.
no, you wouldn't need to incorporate it because it's in a complete other direction. Your shear is acting in this axis here, or that axis there, whereas your pressure is acting essentially in the third axis to everything in the third. Yeah, so I wouldn't apply pressure loads into your shear analysis. Do your shear analysis completely separate, do your bending analysis completely separate, do your pressure analysis completely separate, and then apply them all together to find a failure mode, whether it's applying von Mises or Buckley.
Computer said that I had to take the pressurization load out the shear flow, didn't it? It's just equally complicated.
No, it carries a completely different. The directional component of pressure is completely normal or optimal too. Yeah.
So,
Which one, Chris or Shane?
sorry,
The Indian one or the other one? Oh, Chris. Okay, yeah, I'll tell Chris. Yeah, okay. But yeah, just shear flow analysis is just based on shear.
yeah. Alright, thank you.
Any other questions? How you guys going? Are you guys in the same group or just
No, I've been waiting on a guy to finish the idealization and I've been pestering him.
The idealization.
for your fuselage? Shouldn't be too hard, and it should be a matter of your spreadsheet should be able to. It should be just a plug-in for you. Yeah, you just need the numbers.
I just need to do something.
Yeah, exactly. project, still somehow managed to pass. Even though there was no other component, like there was no individual assignments or tests, or it was all group work, but still somehow. I don't know.
How did you? Oh wait, no, I should be able to. When you made the Excel, would you think we could be able to base this off the Excel often especially for
Well, we made this ourselves, but there was no like.
Yeah, so I think I gave you guys one. Yeah, there was one for one of the questions, but it's going to be completely different. Like the location, the shear, the formulation that I actually went through based on the number of booms I chose, the size of the booms, the thickness. So like the tools we're giving you is just a way for you guys, hopefully, to go away and apply it to your own work. Because it looks like you've like.
Really done everything from scratch.
But that looks exactly what you need. But obviously the formulation of the boom areas is going to be different based on your idealization, depending on like our two idealizations is going to be completely separate, so the formulation is going to be completely separate. So you can't just take any random spreadsheet off the internet that is for boom idealization and apply it to your exact scenario. You have to understand how it works and then apply the geometry to your own scenario.
I also, because there was like load factors, I was thinking like, should we do maximum cases?
For
Maximum load factors on like the
Oh yeah, well that'll be when it fails. So if your aircraft is under max load, like max load factor, you still need to withstand. I don't know if you guys have got up to margins of say you guys cover that briefly at the end. Yeah, so that'll be very important going into like next year's or next semester's design if you're doing 3110. But yeah, basically an aircraft still needs to be able to have come down and landed after it has suffered 1.5 load or 1.5 margin error or margin of safety, on maximum load factor.
So take the normal.
So straight level flight is great for going.
because we only did this for straight level flight.
Yeah, you should definitely be. But what's actually going to change in your?
It'll just be the SY.
Yeah, so your SY and BM, which should be plugins.
Just plug in.
It's just a matter of changing the number in your load spreadsheet, hopefully, because the bending moment diagram is going to change significantly as well. Not just as a factor, like it's not a linear, like shear force is obviously linear with load factor, but bending moment is not. So you need to be very careful.
Oh, because I wasn't sure, because bending moment shouldn't affect it. Because like, if the wings on both sides are the same. Okay.
Yeah, but
There's no bending moment around the.
there shouldn't be. Well, in what axis are you looking at? Like,
Not the.
so yeah. So what sort of bending would be transferred through from the wing to the fuselage? Relative to the fuselage cross section, it won't appear as a bending moment. What other sort of force would it be? A torque. Because you have a bending moment hitting at this axis, yeah?
And then you have another bending moment.
So yes, you're right, they should cancel out. Yes. That's an assumption you can make.
Yeah, I wasn't sure.
But yeah, so in reality when you're thinking about bending moments are going to be in this axis, which will be created at some location along your fuselage.
Yeah, for that case,
You'll have some big lift here, you'll have another lift here, so you're going to get some change in bending moment. Something like that. I don't know. I can't remember exactly. But yeah, you're going to get some bending in that axis, as well as pressure and as well as shear. So just think about, once you convert, like if you have a bending going along this axis, what does that become in this cross section? It becomes a torque. And then vice versa for wings, what becomes, how would you get torque in a wing? Like in a wing box. So you guys have been looking at bending moment, which makes sense for a shape like that. You've got lift going over here, pushing it up, so that's going to create a bending moment. That axis will also create torque around the wing box. What extra do you guys yes, torque, thrust is a good one. Thrust is obviously going to, you have a massive engine down there creating a forward movement that way. It's going to create huge torque that way around that axis, but also the change in lift along a swept wing. The lift center is going to be roughly moving forward on each part. So the lift created here relative to this wing box is going to be torque. And they're going to add up and create more and more torque as you move along. You probably don't need to go into this much now, but that's just something to think about. Like that would be a good one. In fact, the thrust.
I think the wing group is only
Looking,
looking for thrust.
yeah, that's fine though. But so your two massive parts that you hopefully will analyze is going to be the wing root, because bending moment's huge, so you're going to get huge buckling and crippling and all those failure modes you guys are looking at now. And that's definitely going to come into failure analysis. That's like the biggest part of it. And then the engine mounts, because you have a huge drop in shear, so the bending moment is at a relative maximum. But also you have a huge torque being generated.
We have like 2 engine mounts, which is like, so we'll just choose one.
Pick one that's probably the worst, which is most likely the inboard one. It's usually the inboard one. Yeah. Oh, actually no, it could be the outboard one, because the wing section is obviously smaller at the outboard. So it just depends how you want to look at it and whether you want to. And I'm guessing you guys are just taking whatever idealization you did at the root and just applying a scale factor to it. Yeah, that's good enough. But yeah, stuff like that you didn't think about. Obviously, the forces are less outside, but the cross-section thickness of materials is smaller. That's like they design wings specifically that way. So they're designed to fail at every location at the same point, or at the same load. Roughly. Any other questions?
Like you would really wish I was more civil than ever again.
Yeah, I wish I could have kicked him out. Like, we had a chance to kick this guy out from last year at the halfway point, and we decided that we should have. And yeah, same thing. You've got to, I don't know, it's a learning curve.
Much for me, I'd probably do for this.
Yeah. But yeah, you can't. Group work you have to rely on other people, but yeah, you can't. You can play to everyone's strengths, which kind of sucks.
And how are you going to
yeah, I imagine like there will be a submission box, definitely. Whether it is PDF with attached spreadsheets or a OneNote document with links to spreadsheets, or completely up to you guys. We want you guys to do whatever. But in reality, it should still look like a report. There should still be an introduction. There should be a title with the executive summary on the front. An executive summary is really important, because if you've got 100 reports on your desk and you can't remember which one specifically looks at the failure mode on rib 10 of your wing, you look at the executive summary and it says, this report analyzes failure mode, like failure mode to rib 10 of your wing. You go, oh great, that's the exact one I'm looking for. Like, you don't want to have to look through and actually figure it out. Yeah, obviously intro, assumptions, general layout, the report. Not too many in-depth calculations in the middle, but just a general introduction to the concepts you're applying. So you're applying a buckling, how you're applying it. Yeah, hopefully you made assumptions at the start. How do these assumptions affect your buckling analysis?
We probably do this for each section, like the wing would have this and
yeah. And even if you've got other cross sections, like if you're looking at different pieces on the fuselage, different pieces on the wing, pieces on the tail, you should be presenting enough information that we could replicate your work. If we weren't sure of your calculations, we should be able to go into your spreadsheet and actually step through logically and understand why you had that number where it is. And if we don't like the numbers, for example, like it's like in industry, if you hand your work to your supervisor and they at some point want to apply it later but you're not there, the report should be enough information so that they could take your work and apply it completely.
we just use the area.
The areas of boom. Well, you radius of the skin, you'll assume the distance between stringers. You'll assume the areas of the stringers. So yeah, most of it will be assumptions. But remember, your boom area is a combination of the stiffener area and skin contribution from two perpendicular pieces, or three, or depending on the. But yeah, most of it will be assumptions, but it's important to understand what effect those assumptions have on. Like if you increase the area, it's obviously going to increase the IXX, so your apparent bending moments are going to be smaller than reality, for example. Cool. Alright, good luck.
Thank you.
I think here it was still like classroom. So it's still close to the. We're still close to the wall. There were always some classrooms that you got to look at. Some comp labs and stuff. We moved out 2014 to 2015. This building was gone for 2014 and the first bit of. First year, I had a couple of classes, but yeah, that coffee on campus was like, you know, the garden is there. It was like a very vague memory of like walking towards the attic was like eating rice. Yeah, the cafe was like on that side, and there was some classes there on this side.
Yeah, I know you're upstairs where the used to be the toilets. They used to smell really, really bad.
Yeah.
In the classroom, they used to have these wooden tables. I love it.
Working on finding
Happy hours. Last year was better. We had 6 happy hours. No, marker. Like actually on the Tuesday class, it's a chalkboard, so you have chalk in there. Okay. So one folder booklet and another folder marker. The second one you have one chalkboard and one marker board. So just carry markers on Thursday. On Tuesday class, you might need a duster because there's no duster in the class. Yeah. You just need some tissue paper. That depends on which you're doing. I think, I don't know. So you can just go slowly, maybe ask them to solve it. Yeah, but still, personal tutoring. No, many students will still don't understand, like they don't get the hang of it. Even if you quickly discuss in the class, some students will not get it. Yeah. You solved it. Like, I didn't solve it. I just said we could do this, we could do that, and finished in 10 minutes. Because I don't think I didn't write on the assignment. Okay, no, I didn't do that. I just discussed the assignment.
Because question one was really easy too. I didn't tell us how to do it. But I said you can do this.
Yeah.
That part. But all the assignments are very
Hi, everybody. I think our time is up. The next class will come in. So we have to leave now.
是吧？3个。